I'd like to welcome you to the afternoon session of the GA Talks. And we're going to start with Professor John Moores, who teaches here at York. I'm going to say as little as possible because you're not here to hear me. He's a specialist in planetary atmospheres, Mars and Pluto, I believe. And that's what he's going to be talking about. It's something to do with planetary atmospheres.
Well, thank you very much for coming on out, and thank you for the invitation. I always love speaking with the Royal Astronomical Society of Canada and their friends from across the world. So when Randy invited me here, he was asking me for something about planetary atmospheres, something that links them all together and separates them one from the other. So I've given some thought to that and put together a really broad talk that I hope hits some of the highlights and gives you some insight into how planetary atmospheres work and why we should think about them in terms of astronomy. And for me, part of the important part is that really planetary atmosphere is not just because they're the gas in between the geological stuff that happens on the surface and space, but they really link together that exoplanetary astronomy and the planetary science that we do on other worlds. And I put a Juno image up here because it's just so beautiful, I couldn't not. All right, so first of all, from an exoplanetary perspective, why is it that planetary atmospheres are important? Well, basically what it is that the atmosphere itself is the most easily probed part of the planet. And because of that, we can tell an awful lot just by looking at what's in there. So on Mars, we now have a good composition of all the different gases down to about a few parts in 10 to the minus 13, which is an amazing amount of precision for another body. At the same time, things like the transit method, they allow us to observe atmospheres at really incredible distances, not infinite, but really far off. And you can see the an illustration of the TESS spacecraft up here, which is looking for transit around the nearest stars so that we can follow up and study their atmospheres. I wanted to show you as well what a transit looks like up close. So this here, you can see the atmosphere all illuminated. This is actually the atmosphere of the Earth. It's what a terrestrial person would call a limb view, and you can see the sun making the atmosphere shine, and there's a little bit of the moon in there as well. I like to show that because I find that our own solar system and our own Earth is really critical if we're going to understand what our exoplanetary data is telling us. And it seems quite obvious when we're looking at other planets like this, you know, what a planet is. And if you look at this assortment here, this is a chunk of the exoplanetary menagerie from a few years ago. Everything up there, you know, it's the atmosphere we're looking at, and it's the atmosphere that makes it clear to us that these are planets and not just a bunch of marbles sitting on a table. So you might ask, how is it that we know what these atmospheres look like? So for instance, here's a picture of the Earth taken from orbit. And here's a picture of Kepler-62e. Now, I can tell you this probably is not too bad a representation of Kepler-62e. And it's not a view that we can get directly from a telescope or from a satellite right now. In fact, it comes from somewhere else. It is a complete manufactured product, but it's probably pretty accurate because of what we know about atmospheres from our own solar system. Now, from the sort of planetary point of view, and eventually for exoplanetary stuff, the reason we really care about the atmosphere, not only we can sense it more easily than other things, but it encodes the history of the planet itself. So many things that happen to a planet, all of the trials and tribulations it goes through, you can see that in the atmosphere. Things like the carbon cycle, like the escape of water, disequilibrium, maybe even signs of life. And you need to have an atmosphere in your planet if you're going to have some of the more interesting geological processes occurring at all. When we went to visit Pluto, we expected to see a world that was nothing but the husk of sublimation. But the atmosphere was 10,000 times thicker than we thought. And as a result of that, we had an amazing set of geology. And you can see a little bit of the heart here, some of the bubbling nitrogen, and here are the solid water ice mountains. So many things to explore, so much interesting stuff going on. So to give you an example of, if you're not yet convinced that having an atmosphere lends itself to more interesting things, here's a picture of I think this is Gusev crater as photographed by the Columbia Hills. And I want you to take a close look at this one here. Right now, this is the existing view of this place. It's dry, it's dusty, the atmosphere is thin. I can change one thing about this image and make it much more habitable, much more interesting. I'm just going to add some water. And you can see that, I'll point at this one here, that little cleft rock there. This actually is the same image as this one here. So you can see how that makes a difference. This is a nice vacation spot now. So you might ask, if I've convinced you to care about atmospheres, what are they? Well, you might obviously think it's an envelope of transparent gaseous matter surrounding a planet, but don't forget about the clouds, don't forget about the haze, and the way that we define it, it does have a top to it. They just sort of fade away, but eventually the molecules don't feel each other. So at that point, we call an end to the atmosphere. If you're looking at things with a telescope, it's from that top surface all the way down to what we call an optical depth of 1. That's how far you can see into that atmosphere. And the atmosphere, really interesting because it tends to be in contact with the surface. It's telling us the history of the planet effectively. Now, in different wavelengths, in different colors, you can see different distances into a planet. If you look at Titan, just in visible light, all you see is sort of an orangey brown smudge. But if you look at just the right wavelengths, you can see all the way to the surface. And for something like Jupiter, if you look at microwave wavelengths, you can see very, very deeply, several hundred kilometers down, which is what Juno's done. For Venus, you can see the surface with radar. So there's a lot of different ways of investigating a planet and its atmosphere depending upon exactly how you look at it. What different kinds of atmospheres are there? Basically 4 different kinds. You've got giant planets. These tend to be these sort of deep, dense, unprocessed atmospheres. They look a lot like the solar nebula from which they formed. Then you have the thick atmospheres. These ones tend to be more shallow, something like the Earth, where you have a few tens of kilometers, maybe 100 kilometers worth of gas. And Venus is like this as well, so is Titan. Then you have vapor pressure atmospheres. These are thin atmospheres that are in equilibrium with surface material. Mars's pressure goes up and down as the carbon dioxide in its atmosphere condenses and then evaporates. And that's true for places like Pluto. It's true for comets as well. And then you have things that many planetary scientists might not call an atmosphere at all, like the moon, for instance. These are places where the atmosphere is actually stimulated by the bombardment of other particles, for instance, from the sun or from micrometeorites. There's a particular structure that most planetary atmospheres share in our solar system and in other solar systems. And if you take a look at the images on here, I've got Jupiter, so one of those big planets. We've got Titan, which is one of those shallower, thicker atmospheres, as is Venus, and Mars is one of the equilibrium ones. And what you'll notice is that they're all relatively hot near the surface. They get colder as you go up. That's because as the gas expands, it cools. And then eventually they turn over and get hot again. They get hot again because you get radiation in from the parent star, from the sun, and that hits the top of the atmosphere first, so it has the brunt of the heating. And that is a pattern that stays true for just about every planetary atmosphere, except for this weird one here. This is the Earth. We have an extra bump, this one right here. That extra bump comes from ozone. We have a particular chemical in the atmosphere at that level that likes to absorb radiation that the higher up molecules have not yet taken out. And so we have that nice little extra bump there that helps us keep our water over time and really helps enhance the habitability of this planet. There are folks who are looking now for exoplanets that have this same signature, that have this, what we call a temperature inversion, high up in their atmospheres. So now you know a little bit about the different kinds of atmospheres, the type of structure that you have in them. I wanted to sort of explore 4 other parts of atmospheric science with you: chemistry, energy movement, mass movement, or wind as we know it, and how these things all change over time. So if we start with the chemistry, we see 3 different kinds of atmospheres in our own solar system. We've got the hydrogen-dominated ones. These are, by and large, the giant planets, so the biggest slice of the pie there is hydrogen gas. But amongst the other atmospheres, we see 2 different kinds, and these are the more process atmospheres. We see nitrogen-dominated ones, like Titan, which is 95% nitrogen. Here's Earth, which is 78%. And then we see carbon dioxide-dominated atmospheres, places like Venus, places like Mars. There's a reason for that. Over time, atmospheres tend to change. They start out in what we call a reducing state. So if you've seen pictures and artwork of sort of the primordial Earth, this is an idea of an atmosphere that is full of gases that have a lot of hydrogen in them. Over time, that hydrogen escapes, and things with oxygen in them tend to dominate. And so you move from something like this in the early Earth down to something like this, which is more like what the Earth is like today. And all atmospheres tend to do this. If you've got a lot of nitrogen around, the nitrogen doesn't do a whole lot, so it stays and it can dominate. If you don't have a lot of nitrogen, then it's the carbon dioxide and things like that that can really, really build up over time. How does that hydrogen disappear? It's through a process we call Jeans escape. Hydrogen is a very light molecule, it's very small, and so it can absorb a lot of energy when it gets nice and high in the atmosphere. It tends to disappear really quickly. So all that's happening here is this sort of ballistic disappearance of those very light gases. And the longer a planet goes on, the more of this they lose. But don't worry, our nitrogen and oxygen is good for many, many billion years to come. So other things happen in terms of chemistry. We can see other things in an atmosphere from its chemistry. Things like argon and the different isotopes of argon can tell us about how much volcanism there's been. Things like methane can tell us about how much organic material is being deposited into an atmosphere. And we can have things being sequestered, evaporated, all sorts of fun things can go on. And it's really exciting to think that eventually we'll be able to look at these sorts of things in exoplanetary atmospheres and to be able to understand what we're seeing by looking at the atmospheres in our own solar system. All right, so radiation in planetary atmospheres, this is a specialty of mine. I love taking pictures from the surface of other planets, looking at the sun and the clouds and all that fun stuff. And here is an image from Mars Science Lab, which is a mission that I'm a part of. And looks just like a sunset on Earth. You imagine setting out a deck chair, maybe in the Gobi Desert or the Outback, and you're watching the sunset. But it's a little weird. The sun looks kind of blue. If you go away from the sun in the sky, it looks kind of red. So you've got a strange little blue sunset here, and that actually tells us something about the atmosphere that we're exploring. These little particles that float in the atmosphere, clouds and hazes and whatnot, they can interact with light in different ways. You can get the Rayleigh scattering that gives us the blue sky. You can get the geometric optics that gives us our white clouds and our rainbows. And you can get sort of this me scattering that if you were in Toronto about 20 years ago, back when Bethlehem Steel was still in operation, gave us that lovely brown layer that you could see all around the city from the me scattering. We get these lovely effects. All of these different colors come from these 3 different ways of interacting with light. And through that, we can start to get information about the atmosphere through which we're viewing this radiation. Now, how much interaction there is based on this thing that I mentioned called optical depth. And optical depth has a specific definition to it, but really I think of it more in a qualitative way. So I've made a little drawing here for you. Here we have the smiley face star. Not actually a real star, of course. And if you're viewing it without any atmosphere in the way, it looks like a smiley face. Once you increase the amount of stuff in the atmosphere, it gets a little dimmer, it gets a little smudgier. So optical depth 1, that's the point where all the photons coming out of the smiley face star are likely to have at least one interaction with a molecule in the atmosphere or a particle before they get to you. And so you can still kind of make out the expression, but it's getting smudgy. And as you go up from there, then things get more and more blurred away. We can use that with models of how different particles interact to really tell some interesting things about the atmospheres that we investigate. So here's our blue sunset again, as it would appear to a computer. And what I'm showing here is how much red and how much blue. The red line is red light, the blue line is blue light, you would get depending upon how far you're looking away from the sun. Let me paste in the picture, and you can see that the blue dominates when you're close to the sun, and the red dominates further away. So we get these salmon-colored these salmon-colored skies and these blue sunsets when we're going to Mars. And in fact, this is the only way that we know about the dust in the Martian atmosphere. It's too small for us to investigate with any spacecraft instrument we've ever sent to it. So when you're looking at pictures like these, this is an image Curiosity took of the ground. These things are not the dust. Even the flower-like material there is not really the dust. The dust particles are tiny, maybe a micron and a half across, very, very small. Curiosity helpfully provided a piece of plastic debris here for scale, by the way. And even with the microscopes, these little particles in here, these are much larger than the dust itself. We only know about it from looking at how it interacts with radiation. There's a lot of this stuff. Something like 3 million particles per square centimeter if you go all the way through the atmosphere, maybe 10 to the 24 particles aloft at any one time. You take all the dust out of the Martian atmosphere, it would look black at midday. There are other lovely views that we get and other things that we can examine this way. So here's a favorite painting of mine. I just imagine this view. You know, it's a very atmospheric painting looking down at the valley here. And we have this view for a planetary target as well. We have it for Pluto. So here's the limb of Pluto looking back, and we immediately notice a few things, like the layering in here, really spectacular. And we get a lot of light. Because we get a lot of light, we know that we have particles that have to be relatively big. They have a strong interaction. And we see other little things in here as well. This is what we call the specter of the Brocken. You can see the little hills casting shadows off into the distance right on that terminator line. Now, not only is it bright, which tells us the particles are big, but the color is blue, which tells us that the particles are small. That doesn't seem to make much sense. In fact, though, it's a real telltale of processes that we see frequently in the outer solar system. It's telling us we have tholins. So tholins are big aggregates of little tiny particles, nanometers in size, and the aggregates can grow to microns in size. They stick together in this crazy fractal way. So just by looking at an image like this, knowing the color, knowing the brightness, immediately you can tell we've got the same kind of tholin processes at the micron scale that we have in a place like Titan, and we can make these things in the lab on the Earth as well. Now, all of this stuff moves around. So one question that I always ask my students is, why does air move? And just to let you know, if you ever take one of my classes, the answer is pressure. So if the pressure is low, air wants to move towards that low. If it's high, pressure drives air away from that high. And if that were the only thing, whenever the sun was heating the surface, you'd have air rushing away, and whenever you had nighttime, it would be the opposite. But there's something else that happens on planets. Planets are rotating spheres, and so there's an additional force that comes into play and gives us all of these lovely circular features on a weather map like this. That additional thing is Coriolis force, and that's something that comes just from the fact that the planet is spinning. If you want to think about this, imagine if you had a frictionless planet and you were sitting at the North Pole. You have no angular momentum at all. Suddenly, you start to roll down the hill, you head towards the equator, and you start falling behind the planet's rotation. If you were glued on the planet, watching this frictionless ball come from the top, you would say, oh, it's going to the west, more and more as it gets closer and closer to the equator. If you start at the equator with a lot of spin, as you move towards the pole, you seem to outpace the planet. And it's this kind of combination of pressure and this this Coriolis force that gives us what's called geostrophic wind. That's what a hurricane looks like. So what it really means is that if you don't have big differences in temperature on a planet, that doesn't tend to drive a whole lot of winds. And that tends to go hand in hand with low pressure differences on a planet. You look at a place like Titan, Titan doesn't have much wind at all because the coldest place and the warmest place are less than 1 Kelvin different from one another, less than 1 degree Celsius. I can tell you what the forecast is for Titan now and for the next few million years. And I'm going to be even better than the Weather Network at this. So that's one thing that tends to happen an awful lot. It also means that on planets with very low pressures in total, you don't get very high winds. I love my geologist friends. They love to tell me about these great big seasonal windstorms on Mars that just tear up the landscape. They don't exist. It doesn't happen, which is unfortunate because I love this painting. What you do get is greater organization as you increase the spin, as you pump up that Coriolis force. And for the Earth, what that gives us is this large-scale structure where you have cells and jets. So we in Toronto, of course, are very familiar with the jet stream. We like it to stay north of us so that we can have some nice warm air from the south. Not so great when it goes below us and we get to have air coming to us from the Arctic, especially in the wintertime. So on the Earth, you end up with sort of 3 cells in each hemisphere and a total of 6 bands in all. And what I'd like to convince you of is that this kind of structure that we see on the Earth is exactly the same thing that we see on a giant planet. You can't see it in quite the same way as you would in a giant planet, but if you look at where it's dry and where it's wet, you'll notice that you can pick out each one of these cells. Look at this, where the Sahara is and the desert down in South Africa. If you follow that across the globe, you can actually see the banding, and it's exactly the same reason that a place like Jupiter has banding as well. If we go over to Jupiter, Jupiter turns on its axis every 9 hours and change. And so it's doing this spin much, much faster than the Earth is. What that gives you is a lot more of these bands, a lot more of these jets. And you can see this picture. This is actually from Galileo data. You actually wind up with 31 of these different zones back and forth. Galileo wasn't able to see what's up here at high latitude, so there be dragons. And the dragons look like this. So we have these 5 storms that constantly rotate around each other at high latitudes on Jupiter. It's really, really wild. So you can put this together and you can create sort of a picture of what a planet should look like in another solar system based only on how quickly it rotates. So if you're like Jupiter and you go around quickly, lots and lots of bands. If you're like the Earth and you go around once a day, then you only get a few bands. And for a terrestrial planet, mostly you see that on the surface. If you're like Venus and you orbit more quickly than you rotate, then you get no bands, basically. You get this interesting chevron-y feature. All right, so the last thing I wanted to talk about was how these things all vary with time. And there's a couple of different time scales that are very important for us when we're thinking about how things vary on a planet. So one of the strongest drivers is what we call the diurnal signal. So that is the rotation of the planet coming into the view of the star and out of view of the star over the course of its day. So we already know it's typically cold at night and warm in the daytime, and you can get things moving around in the atmosphere with that same periodicity. This is data from the Phoenix mission here. What we saw at night with the LiDAR is you would get these ice crystals, these clouds that would fall down. Eventually they'd make it very close to the surface, and you could light up the fog with basically a searchlight. This is the Phoenix LiDAR here. I was using it as a $60 million flashlight, by the way, in this image. So you can see those particles get really close to the surface. You can see them settle out on the surface as fog. And when we dig into the surface, you can see how that water actually makes its way in before evaporating out again. So there's this cycle that takes water from the surface up to 4 or 5 kilometers of height where you can see it from vast distances with transit. By the way, here's what clouds look like on Mars. This is sort of my day job on Curiosity, taking images of these things so that we can track how it changes on diurnal and longer time scales. But these are lovely little 6-minute animations of what the clouds look like at Gale. You can go up to longer time scales, more than a day, but less than a season, what an atmospheric scientist would call the synoptic or storm scale. We have lots of examples of this on the Earth. There are examples on Mars, but I just love these ammonia ice clouds from Saturn here. You have a storm that just takes off and just generates these things, dredging things up, freezing them out, and then you see this lovely ephemeral band that shows up on Saturn every few years. And then we have seasonal things going on. We know of the seasonal patterns on the Earth, but it can be more extreme on planets that have a strong eccentricity in their orbits, like, for instance, Mars. So with Mars, we've got a 9% eccentricity to its orbit, and that means that its orbit has just as much effect on what's going on seasonally as does the axial tilt, which is very similar to the Earth at 25.4 degrees. Because of that, we actually see the pressure of the atmosphere on Mars go up and down over the course of the year by more than 30%. So this is what's been seen at the MSL landing site, also at Viking, and you can see that this goes up here over the course of the year to maybe 900 pascals. It's about 9 millibars, down to 700. And different places see slightly different amounts of this. It causes this great change in the polar caps. So here's a couple of views from the Hubble Space Telescope looking at the northern part of Mars. We've got what we call the residual cap in here that is exposed in the summertime. And you can see sort of this, this is all dunes around it that get exposed. And then in the wintertime, you get this deposition of dry ice. Much of it falls as snow, and it can be up to about 1 meter thick down to about 60 degrees north latitude. And when I tell my students about this, they're always shocked that you could get a process like this, you know, where it just expands and it snows out and you get 1 meter of carbon dioxide snow. Well, we do the same thing with water, of course, on the Earth. And it goes much further than 60 degrees north, unfortunately for me. It means more shoveling that I have to do, as opposed to the Mars rovers, which are well away from this. We also see variations over longer time scales. Mars of today, kind of a dry world, a few clouds around the equator at certain times of year whenever they get lifted up over top of the mountains. But if you go to Mars of the past, there's a chance that you actually had some liquid water. Well, if you go far enough in the past, there's definitely liquid water. And these climate cycles on Mars can last hundreds of thousands of years, going back and forth and back and forth. In fact, that record is something that we can see. When we look at the banding in the northern cap, it actually does a really good job of following how much light, how much energy is being received by the cap. And in this graph down here, all that the authors have done is they've taken this picture of the northern cap and they suspend on top of it exactly how much light should be received. And the bands actually match quite well. It's almost like reading a record. So if you go to the really long term, you want to go back 3 billion years, you get these wonderful vistas from MSL. So here we are looking towards Mount Sharp, down into the lowest part of the moat that it lies around the central mountain. And what you'll notice is all of these rocks here are what a geologist would call dipping in the same direction. And you can follow them along the way. The reason you can follow them is because what you're seeing here is an ancient shoreline. This used to be full of water 3 billion years ago, back when we had a nice thick atmosphere, like I mentioned at the beginning of the talk, that allowed that water to be liquid, that allowed lots of interesting things to go on. So I'll leave you with another lovely picture from MSL. This is Phobos. Again, this is kind of the exotic wrapped in the familiar. The crescent moon here, that is not really a perfect crescent, more rocky, in a blue sunset. So it has everything in it. So what I want to leave you with is this idea that much of planetary and exoplanetary science, we're concerned with atmospheres, we're concerned with environmental conditions. If you want to find life, you've got to find water, you've got to find an atmosphere to keep that water liquid. It all goes back to the same thing. And really, our terrestrial, our solar system experience, it can be a guide for what we see when we look out to other exoplanetary places. But we should expect surprises. We should expect the exotic. And we should expect, actually, to learn more about our own solar system as well from what we see out in the broader universe. So once again, thank you for inviting me to speak. And with that, I'm happy to take any questions you may have.
Frank?
Working now? Okay. So a question about this equilibrium on Mars caused by methane. And so a couple of your slides mentioned or referred to the possibility of methane, and one even mentioned some researcher by the name of Moores might know something about it. So I'm just curious because it used to be up till a few years ago considered a possible indicator of bacterial activity that might have been causing the methane. And so maybe you can provide an update on it. Furthermore, as an extrapolation, you mentioned that Mars has light winds compared to some other potential planets with differential heating, with stronger heat. So the question would be if there's similar emissions, small emissions on other exoplanets from potential life sources, would they be obliterated or diluted too much for us to detect in cases of strong winds?
All right, that's a big question. So in terms of methane, I'll give you the short version because you probably don't want another 60-minute talk right now. So at least not by me. So in terms of methane, there is a thought that if you had a lot of it very early in Mars's history, it could have helped keep Mars warmer than it is right now, and than it would have been back then, because the sun would have not been as bright 3 and 4 billion years ago as it is today. Today, methane is a very, very trace gas in the Martian atmosphere. It's down at the sub-parts per billion level. So it doesn't affect the climate, but it may be telling us about processes that happen in the interior. I suspect very strongly that we have methane seeping out of the interior today, and there's something in the subsurface that's creating it. Could be microbial, but could be geology, could be ancient methane being released from clathrates or something like that as well. You'll just have to wait till my paper under review at GRL comes out, and then I can tell you all about it. So there's still exciting things going on in terms of methane. In terms of light winds, just really quick, so we tend to find the more powerful winds further out in the solar system. The speed record is Neptune with 2,400 kilometers an hour, and Neptune has a very deep atmosphere.
Thanks very much. I enjoyed your talk. On the North Pole of Saturn is a hexagonal-shaped storm. I've never understood it, and I never understood why such sharp vertices. Can you give me a simple explanation of why that shape came to be and persist?
Well, I guess if you wanted, really succinct, I would say fluid mechanics. But it's a complicated problem, and it's one that my friends who do a lot of fluid mechanical modeling have really sunk their teeth into. I don't recall off the top of my head what the solution is to it, though I think that they have got it pretty much figured out. It's basically the same sort of thing as you get with Jupiter, with the 5 storms in that pentagonal shape, and they stay in that pentagonal shape as well. So Saturn is kind of transitory between the kind of behavior we see on the terrestrial worlds and the kind of behavior we see on Jupiter. So imagine those 5 storms sort of smushed out a bit, and you can get these kind of rounded corners and straight edges. But it's really wild, and you can actually do this with a turntable as well. If you set it up just right, you can create hexagons as well.
Thanks so much, Joe.
Oh, thank you.
We have to show everyone your print.
Oh.
Rings of Neptune. There you go. Thanks very much.